Is it okay?
Yes.
So it's the presentation, yes? Not the...
Yes. You have 25 minutes.
Okay, I can start. Yes?
Yes.
Okay.
Thank you.
So yes, so thank you very much, and thank you very much for the introduction, and especially for organizing this whole conference. And I'm so happy that we can, even in such difficult times, we can meet all together and discuss our results. So what I would like to focus today is such a structure. So in principle, the microcavity with two distributed Bragg reflectors that can confine photonic modes inside. And then inside we can put also an emitter, for example, an exciton in a quantum well or a different type of material. And now I would like to modify the structure for the different means to demonstrate you how we can actually engineer different type of couplings and different type of synthetic fields that will act and that will appear actually in such a structure. So first, if we act on excitons, so we know that the excitons are very sensitive to external field, for example, electric field or magnetic field. So if we would like to observe the splitting of the modes, so for example, the splitting of the polariton modes or even photonic modes or exciton modes, we can apply external magnetic field, and then what we observed. Oops, I cannot change the slide, I'm sorry. Oh, now it's okay, yes. So give me a second because I cannot see my presentation. Okay, perfect. So when you apply magnetic field, when you can really play with this and split the polariton modes and make fully polarized polariton branches, fully spin polarized polariton branches. Yes, but this is the play when we play with the excitons. But what happens if we can actually act on photonic modes? And this is what actually I would like to focus on. So we can change the photonic modes, for example, like building the photonic lattice, and there are lots of very beautiful results in the literature when you can make the polariton spin filter or propagation really of the polariton modes on the edges of such a structure, of such a honeycomb lattice, when really the spin of polaritons is strongly coupled to the momentum. So we can have edge modes of given spin polarization and other spin polarization. So this gives us this very beautiful engineering of photonic modes into the lattice, into the photonic lattice. But there is another effect actually that I would like to discuss today. It's a spin-orbit coupling, because the spin-orbit coupling, even in the planar cavities, will allow us also to couple the spin of the photon, which means the photon polarization, the circular polarization sigma plus or sigma minus, with its momentum through artificial magnetic field acting only on the polariton modes. So first, of course, this optical spin Hall effect was developed by Alexei Kavokin, and it was discussed in the context of exciton polaritons. And here you have the very beautiful results when really the photon momentum in the reciprocal space, you can see this very nice quadruple pattern, when the photon momentum is coupled to its spin, that you can have the sigma plus polarized modes and the sigma minus in the different momenta. So it was discussed in the context of exciton polaritons, but then it was also demonstrated in the group of Pavlos Laboudakis that actually it is a purely photonic effect, and it can appear only in the pure cavities without any excitonic modes inside. And this is due to TE-TM splitting. So the TE-TM splitting is the origin of this effect, because in the cavity, when we look, when the modes are propagating, so TE and TM modes are propagating with a different momentum, and we observe the small splitting of the modes, because this both modes feels different effective cavity length inside the structure. So for this TTM splitting is very peculiar, that at k equal to 0, there is no splitting of the modes, but when we increase the wave vector, we see the small splitting of the modes. So that's why actually it produces such a quadruple pattern. But now what we can do is we can further modify this optical spin Hall effect, and not only introduce into the structure TE-TN mode splitting, but we can add also some structure anisotropy. So if we will put inside the cavity some anisotropic media, so for example, like here, it was demonstrated in this very beautiful work when you put the two-dimensional perovskite that has a difference in the refractive index is in the extraordinary and the ordinary of some given value, that actually what you can produce is the small splitting even at k equal to 0. So additionally, you add to the TE, TM splitting at high wave vectors, you also add the small splitting at 0 wave vectors. And actually it can lead you to the crossing of the modes at the given point, and very special splitting of the modes and the splitting of the photonic parabolas in the momentum space. So then when you look in the kx and y momenta, you see the the very special pattern like of the two circles and the points when the two parabolas they touch, and these photonic modes have very special polarization pattern that I will discuss further on in my talk. But then the story doesn't end. So what can we do more actually? So apart from the TE-TM mode splitting and the structure anisotropy, we can add also external magnetic field. And then this produces, as you already, the whole different type of possibilities. And also what's demonstrated actually in this publication, that you can have very nicely spin polarized photonic branches in the momentum space, even with such a nice anti-crossing at the given position. So that was the theoretical model, and realized experimentally in semiconductor samples with where the external magnetic field was actually acting on the excitonic component in the polariton mode, and then the non-zero baric curvature can be produced inside such a planar structure. So this is very, very important effect. And then we can apply, of course, a different materials inside the structure. So I mentioned one already, the perovskite, but then the perovskites, it was demonstrated in the group of Daniele that actually in a high magnetic field, when this high magnetic field breaks the time reversal symmetry, and then you can produce such a small splitting between this very special particular crossing point in such a structure. And then I hope that we will hear more during this conference about these very beautiful results, because the whole morning session is sort of devoted to the spin orbit coupling, and I'm really looking forward to look at it. And also about this very, very beautiful result when in the cavity the parallel was placed, and the parallel is characterized by the very high anisotropy, and this really can also produce such a splitting of the modes and the anti-crossing. So this is what I think that the results that are very, very, very important up to now. But I would like to put your attention also on another effect, which is the Rashba and Dresselhaus field, which was first, or Rashba and Dresselhaus spin-orbit coupling, which was first discussed in the context of semiconductors for the systems that are lacking the inversion symmetry center. And it was demonstrated that actually it can be such a term that couple momentum as spin can be realized in the system that splits the two photonic branches in the momentum space on the given momentum. So we have two purely polarized photonic branches, and then the minima appears in the different momentum. So in the reciprocal space, it looks like such a circle. And this will be very peculiar realization of this Rashba and Dresselhaus spin-orbit coupling, and I would like to demonstrate you how we can make it in our structure. So what we are investigating in our group is microcavity. So we have two distributed Bragg reflectors, but what we put inside the structure is actually a liquid crystal. And the liquid crystal is, you can imagine, is an elongated molecule that we can tune the difference between the extraordinary and the ordinary refractive indices. We can tune from 0 to 0.5. 0.4. I will show you in a minute how we can do it. Yes, but this is our whole structure. So bottom DBR, top DBR, there is a polymer layer with a special rubbing that allows us to orient the liquid crystal molecule at the initial condition, and then we can add to act external electric field through this ITO electrodes, and we can reorient the liquid crystal molecules. And actually, this is how our structure look like. And the whole structure is fabricated in Poland at the Military University of Technology in the group of Professor Victor PIETKA. And so how does it look like? So this is the scheme of my structure. So I have one DBr, the second DBr, and the elongated molecule of liquid crystals kept here. So if we look at the single molecule, then we can distinguish different directions. So we have the ordinary refractive index that is here in this vertical direction. This is extraordinary. Ordinary here and here, and then along this this molecule we have the value of extraordinary refractive index. So then if we put the molecule inside and we apply electric field, we can rotate the molecule in plane, so versus the DBr here. And then what we do actually, what we do actually is that we change the position of the molecule versus the propagation versus the wave that is propagating here, and our wave field then the different value of refractive index, and actually it can be tuned in the whole range. So now I will play you the movie that you can. I will play you the movie when you can observe now that we apply electric field. So we start with the small splitting of the T at the M mode and this orientation of the molecule. And now I rotate the molecule, and then you see that one mode stays, and then the second mode is coming, and then this mode pass, and then again the new mode comes into play. So I will do it maybe once more. Okay, so let's start again. So at the initial condition, we had only TE-TM splitting. Then you apply a small electric field when the molecules start to tilt a little bit, and then we shift one of the photonic mode, one of the component into a different energy. And then if we play again with this, then it's this very special position when we cross the second mode with the first mode, when the two branches split. And then when we rotate again, then we come to a different regime of this mode splitting. I would like to show you how exactly look the polarization splitting of the mode. So I will have here a movie again, the same results here. So this is the reflectivity from our structure, but here you will see just the reflectivity from the structure, and you will see now the polarization component. So S1, which means the H and V polarization, S2, which is diagonal and anti-diagonal, and S3, which will be the degree of circular polarization of the mode. So for example, if we start with such initial condition, we see that we have one mode that is polarized, that is V polarized here. And now if we apply electric field, so we turn out the molecule, we see that the polarized, linearly polarized mode comes, and at a certain moment actually we lose this polarization and we observe the purely circular polarization, and then we go out from this resonance, our structure is once more linearly polarized. So I can play this movie again. So in the structure regime, we mostly have our linearly polarized mode in all of this regime, but there is a regime when different modes come, and actually we have purely polarized system with a very special type of this polarization pattern in the circular polarization basis. So this is the to have a more insight into the structure. So I will demonstrate you how look the shift of the photonic modes in when we rotate the molecule. So we have many modes in our structure because we have a thick cavity, and that this thick cavity, for example, when you concentrate on this mode, we observe that we have the V polarized mode that is actually do not change when we rotate the molecule, because the V polarized mode is along this ordinary index. So our wave field is ordinary index that doesn't change. But then when we change the rotation of the molecule, we shift here in this direction like here I have marked the theta. So then actually the H polarized mode is modified and feel different refractive index, and that's why it is shifted here in energy. So there are the regime when the modes can cross, and there are many regimes, for example, when we can cross the same mode of the same parity with the modes of the different parity, and then the second crossing of the mode with the different mode number, but again with the same parity. And now I would like to discuss these three different regimes. So when we start with this regime, this is the very typical regime that we know from the semiconductor, for example, a structure where actually the molecules are oriented perpendicularly to the surface. And what we observe is the small modes splitting here due to the TE and TM splitting of the modes. So this is this regime, and this is we overlap the same mode with the same mode of the V polarized mode and the same mode of the H polarized mode. So the same mode number and the same parity. So this typical regime, as I told you, we can observe when we look at the resonant transmission, we can observe this beautiful spin Hall effect. So the coupled sigma minus and sigma polarized mode in the momentum space with such a quadrupole pattern. But then if we rotate slightly the molecules, what we can observe actually that we can modify this quadrupole pattern and make such a spin texture in the momentum space. So we make such a spin whirl in the momentum space, but only because we can rotate these molecules and introduce slight anisotropy inside the structure. So then if we slightly rotate a little bit more molecules, so now we go to now we rotate them just to introduce really this anisotropy in the structure, so even the splitting at k equal to 0, we go to the regime where when we can have the two modes that they actually cross at a given point. So here you observe, I have plotted the two parabolas. So they are so then we have the parabola of the upper parabola and the lower parabola here in this blue. And you can observe that there is this actually points that when the two modes are touching. And actually these are the really points. So if you plot the difference between now this yellow and the blue parabola, what we observe that actually these are these very special diaboical points or conical points that are discussed in the literature, that we have really the linear crossing of the modes. But there are 2 points of the given energy, and really actually the splitting drops, the energy difference between the two modes just drops up to 0. So, and this is actually the realization where we have both the TE-TM splitting and then the structure anisotropy. Here I would like to show you how does it look like once more. So we are again in this regime when we have just 2 touching points, and now when we can make the resonant transmission for our structure, so you see that actually you have these 2 parabolas, they are touching, and then if you continue energy, then then you have the splitting again of the modes, and then you finish off with just the 2 linearly polarized modes, the inner and the outer. So that is our model, and this is our experiment actually. So in the cavity, so now we just tune, only we look in the momentum space, and we tune the energy, and we observe in the tomography, we observe the different modes, and we really have the momentum when the 2 modes are touching on this very special point. But all the time, the modes are sort of mostly linearly polarized. Yes? So the circular polarization degree is really very, very weak. I have the results, so if someone is interested, I can show it in the end. But I would like to jump to a different regime, because really this rotation of the molecules and this special type of the structure allows us to change to a different regime. So now I would like to jump to this regime, where we can cross the modes of the same parity, but of a different number. So parity is the same, but the number is different. So we have n+2 mode crossed with the mode of number n. And again, we have this crossing of the 2 parabolas. But now, actually, when we plot this in the space in the kx and the ky in the two-dimensional momentum space, then we observe that when we make the difference between this upper parabola and lower parabola, between the two modes, actually what we have is not two, but already 4 conical points, but now they have the 2 points, and the other 2 points are at a different energy. So again, we have touching of the modes, but they are at the different energy, but for conical points. So now what I describe, just to summarize a little bit, is these two regimes. What I showed you, that we have the regimes of the typical spin Hall effect, so that when we have only the TE and TM splitting of the modes with at a given momentum with zero splitting at the key equal to 0. And then we have the other regime when you cross the mode n+2 with the n of the same parity but of a different mode number, where we introduce such a small splitting. And actually what we are able to do, we are able to derive such a Hamiltonian that will describe us the both regime. So this is valid for this regime of the spin of the typical optical spin Hall effect, and this with a higher mode number. But then we can parameterize our structure with these delta parameters that actually describe the birefringence in our structure. So in this case, in the typical optical spin Hall effect, what we put here is we have all of this delta are actually the same, and they are higher than 0. And then the mode splitting, so the difference between H and V polarized modes, so this X-Y mode splitting here in this regime is 0, so we put 0 here. And then we have the typical Hamiltonian that was described, that was first developed by Alexei Kavokhin and then later developed by many authors to describe the system. But if only we will play with our birefringence and with our dielectric material, then we can go to the such regime when actually the delta E will be smaller than 0. Then all of this delta will mean something different. But we can also plot this effective magnetic field now that acts on in plane of our structure, and this now you can see how it is oriented. Okay, so this is a little bit very.
Barbara, you have 3 minutes left approximately. Okay.
Really? Okay.
Yes, really.
Okay. So I'm sorry, because I should have our. Okay, no problem. Okay, it's okay. Okay, but then I have the regime here of the mode coupling here when we have n and n+1 mode coupling, so 2 modes of the different parity, and you observe already that we have the very nice splitting of the modes and splitting in the momentum, and this is called this Rashba regime, Rashba Dresselhaus regime, when actually we have this yes, when our structure gives us the possibility, because you can tune the mode. And in the Rashba regime, when we can observe that when we slightly tune the molecule, so of course we approach to this regime when the modes touch, and when we go beyond this point, we have the anti-crossing, and this anti-crossing here is actually when we look at the different momentum, we know that the splitting of the modes scales linearly with the wave vector. So this allowed us really to, so maybe this I will skip. Oops. So this, yes, so I'm sorry, I was just feeling the pressure of the time now. So we have the linear splitting between the modes, and then when you make the cross section between the modes, where actually we see that we have the 2 parabolas and the 2 rings that approach, and the modes start to overlap, touch with these points, and they have the 2 circularly polarized modes. So if we make the cross section, we have the 2 parabola. One is sigma plus polarized, the second is sigma minus polarized, and they are splitted here in the momentum space. And now there is this Hamiltonian that actually demonstrates you this linear splitting of the linear splitting with the momentum. This will be this Rashba Dresselhaus term. So here now in this particular image, we have this X, Y modes equal to 0. So that's why the modes are touching. And then we have the pure Rashba Dresselhaus Hamiltonian, but we can of course turn our molecule and introduce this this additional term and be around this very special points. And really our Rashba parameter scales with the difference between our extraordinary and ordinary refractive index value. Then, of course, what we can do further, we can put the organic dye in the cavity and observe this already in the emission process, observe this Rashba and Dresselhaus field. We can put the perovskites in the cavity, in the liquid crystal cavity, and also we have the very special mode splitting with sigma plus and sigma polarized modes separate in moment of space. What I didn't tell you is that in the real space, actually, the different regimes in such a cavity corresponds to a different spin texture, like a half skyrmion, that are called merons. So we can observe second order meron, second order antimeron, and in this Rashba and Dresselhaus regime, we can observe the persistent spin helix. So I hope that one day I will be able to describe you this regime as well, and this spin texture as well. So before I conclude, I would like to thank all of my team. I'm really grateful and I'm really happy that I can work with them. So especially Jacek Szczytko, Kasia Rechcińska, Mateusz Kurur, and all of our students that actually join our group, and we work all together, and all of our collaborators, that especially the Military University of Technology and the group of Professor PIETKA that produces this special type of microcavities filled with liquid crystal, and our theory that we discussed a lot with Michał Matuszewski, Witold Bartoszewski, and Pavlos Lagoudakis and Helgi Sigurdsson. So this is my summary, and yes, thank you very much for your attention.
Thank you very much, Barbara, for this very beautiful talk. So it's now time to ask questions. So remember, if you want to ask question, raise your hand. Okay, it's a test. Is somebody going to find the button? Or everybody is just sleeping? Okay, we have a question by Dima Solnishkov. Okay, you can go. I'll cut my microphone.
Well, in fact, if somebody else has a question, of course, you can ask first, but it seems like that nobody has, so I can ask mine. In fact, I would like to, to ask if you can explain qualitatively and briefly your point of view, your understanding, how does it happen that in the microcavity with purely linear splittings, birefringent materials, you have circularly polarized modes in the end, because at least at some non-zero wave vectors, you observe some circular polarization. So how does it happen qualitatively from your point of view?
Okay, so okay. So qualitatively, actually, without the use of the Hamiltonian, yes, and without the use of the symmetry, so...
Well, maybe with the use of the symmetry, there are maybe some very simple symmetry arguments, whatever you prefer.
Of course, the whole Hamiltonian you can derive from the symmetry, yes? So you can take the Hamiltonian and then you can look what is actually the electric field when you look at the electric field distribution. So what we did first, we took just the waveguide approximation, and then we really propagate the electromagnetic wave in the through like the Maxwell equation through our structures. Yes. So then you can see, and then from this hand waving argument that you can when you look at the molecule and how they are rotated and how does effective field they see. So this you can all derive all of this Hamiltonian. So to have this Hamiltonian, you can approach in two ways. So one will be the full Maxwell equation with the KP model that you can derive in the vicinity of this point, and then you can observe this mode crossing. And then also you can look to which symmetry, so the momentum and the spin of the photonic mode actually will couple. But I'm afraid that I don't have the simple explanation.
Well, thank you very much.
We have a question by Nikolai Gipius. if you want to speak,
Nico.
Thank
you very much. Very beautiful talk. I have a short question about this speed. How quickly can you rotate your molecules by external electric field?
No, so no, this is not a very efficient. So this we cannot quickly rotate actually them. So we just apply electric field, and then I don't have the value actually here, but this is slow process. So this you just apply the field, but you see it, but you cannot manipulate on the on the very fast, like the frequency that you can really make the fast operating device on this structure. So this I wouldn't say that you cannot rotate it fast.
Thank you very much.
Hello. My question is concern the Rashba Dresselhaus Hamiltonian, and I would like to ask if in your system you can tune separately the Rashba and the Dresselhaus coupling, or you can only produce in the experiment the configuration where the Rashba and the Dresselhaus coupling are the same, and therefore you are already at the spin helix persistent point.
Yes, this is actually what we do. So we can produce only this position when we have the Rashba and Dresselhaus terms equal, and the persistent spin helix. Yes. So we cannot change the two.
Okay, thank you.
Okay, so there are no questions left. So thank you, Barbara, again for this very nice talk. Don't forget to deactivate the sharing screen.